Okay, I may have touched on asymptotes earlier in the course, but I like to talk about them deeper when we get into this chapter. Um, Examples of infinite limits here. When we say infinite limits, we're actually talking about what happens to a function where a function goes to infinity or negative infinity as x approaches a number. So if you take a look at the graph of this function 10 over x minus 2, notice that as you approach 2 from the left, notice that this function decreases without bound. So therefore that's an infinite limit because the limit of that function equals negative infinity, which of course still does not exist, but we can say it's negative infinity. And then if you approach 2 from the right, notice that the limit increases without bounds, so we can say the limit is infinity. Now, in this function, actually, if you approach 2 from the left, you're going to get infinity, and the limit for the limit, and the limit of the function as x approaches 2 from the right also is going to go to infinity. So actually, the limit, the left-hand limit as x approaches 2 is infinity, and the right-hand limit as x approaches 2 is infinity. But remember, just because we say the limit is infinity, it doesn't mean the limit exists. It's just a special way to say that the limit does not exist. And here's another one. This one actually has, like, here's x equal 2 minus 2, and here's x equal plus 2. And so the limit as x approaches negative 2 from the left is negative infinity. See how it's diving down? And then as you approach negative 2 from the, let's see, make sure I got the right one. That should say, here it is. Okay, I'm sorry, I said this wrong. The limit as x approaches 2 from the left would be negative infinity, and then the limit, I said it right, I just said it for the wrong one. The limit as x approaches 2 from the right would be this piece, and so that's going to go to plus infinity. Now for negative 2, the limit as x approaches negative 2 from the left would be over here. So as you approach negative 2 from the left, you're going to go down to negative infinity, and as you approach negative 2 from the right, it's going to go up here to plus infinity. So that's infinite limits. So you're going to get a vertical asymptote anytime the function approaches infinity or negative infinity as x approaches some number from the right or left, then x equals c is called a vertical asymptote. So actually, if you go back to these, on this one, x equal 2 is a vertical asymptote. Same thing over here. X equal 2 is a vertical asymptote. Here, x equal negative 2 is a vertical asymptote, and x equal positive 2 is a vertical asymptote, because those limits go to infinity or negative infinity as x approaches those numbers from one side or the other. So let's talk about the existence of a vertical asymptote. Suppose f and g are continuous functions on some open interval. And let's suppose that the numerator does not equal 0, okay, at c, but the denominator does equal 0, and g of c equals 0, and there exists an open interval c such that g of c does not equal 0. I know this is a little confusing, but they're just saying that let's say right here, see, this function equals 0, the denominator equals 0 at x equal 2, but around x equal 2, the denominator doesn't equal 0. It actually has values. But what we're saying is, at x equal 2, the denominator is 0, but around x equal 2, it doesn't equal 0. So that's all they're saying. Okay. So basically, long story short, you can almost sum it up as saying as long as the numerator is not 0, but the denominator is 0, you're going to get a vertical asymptote at that number. So for instance here, 3 over x minus 5, well, I know x equal 5 makes the denominator 0, but it doesn't make the numerator 0, so x equal 5 is a vertical asymptote. This function, notice I factor the denominator, x equal 4 makes the denominator 0, and since it doesn't make the numerator 0, it's a vertical asymptote. X equal -1 makes the denominator 0, but it doesn't make the top 0, so therefore that's a vertical asymptote. Now this one, notice I got it factored here. X equal -3 makes the denominator 0, but it doesn't make the top 0 because that would give you a -6 in the top. So x equal -3 is a vertical asymptote. But the reason x equal 3 is not a vertical asymptote is because x equal 3 makes the denominator 0, but it also makes the numerator 0. And you might remember that's where we get holes. So you can do this one as practice to find the vertical asymptotes. Okay, so let's talk about finding holes and infinite limits, and let's talk about let's decide if we get a vertical asymptote or a hole at certain values. So for this problem, I'm going to factor it. It actually factors into x plus 4 x minus 2 over x plus 2 x minus 2. Well, if x is -2, the denominator is 0, but the numerator is not, so I'm going to get a vertical asymptote. But at x equal 2, the denominator is 0, and so is the numerator, so I'm going to get a hole. Okay. So now this one, you can skip this one. I'm not sure why these got put in here. I should have removed them because we don't do trig. Okay, so now the way you evaluate limits, let's evaluate the limits and confirm it from the graph. Okay, so let's see if we can get the limit of this function as x approaches 1. Okay, from the right. See that plus? From the right. So 1 from the right. So, well, we know since 1 makes the denominator 0 but doesn't make the top 0, then the limit's either got to be infinity or minus infinity, what I call the infinity twins. So it's got to be one of the infinity twins. So to figure out which one it is, let's just plug some numbers close to 1 in from the right, like 1.1, 1.01, 1.001. Well, I can see that as I get closer and closer to 1, the y values get larger in the positive sense. So this limit must be positive infinity. Now, if I approach 1 from the left, well, let's plug in numbers close to 1 from the left, like 0.9, 0.99, 0.999. Well, there you can see the numbers are getting to be large negative numbers. So that means from the left it goes to negative infinity. And if you look at the graph here, this vertical line would be at 1. And notice from the left, the graph is going down, and from the right, the graph is going up. Thus, as you approach 1 from the right plus infinity, you approach 1 from the left, you get negative infinity. Now, if you investigate this one in a similar fashion, what you're going to find out is that there's 2 places where you get a vertical asymptote, at x equal 2 and x equal -2. So here I'm saying, what is the limit as x approaches 2 from the left? So notice I plugged in numbers close to 2 from the left, and notice the y values are getting larger. So I'm going to say the limit as x approaches 2 from the left is plus infinity. Now, if I want to know about what happens as I approach 2 from the right, I'm going to pick values that are close to 2 from the right, 2.1, 2.01, 2.001, and then notice I get large negative values. So as I approach 2 from the right, I'm going to get negative infinity. And if you look over here, you can see here's the graph, and these vertical lines are the asymptotes. So as you get close to 2 from the left, you're going up, so plus infinity, and as you get close to 2 from the right, it's going down, so it's going to negative infinity. And also you can check what's happening as you approach -2. Notice from the left, it's going to plus infinity. As you approach -2 from the right, it's going to negative infinity. Okay, now I want to talk about limits at infinity. Now you can read this yourself. Just pause the video if you need to. But basically, a limit at infinity means the limit as x approaches infinity is equal to some real number. So here's the graph. And notice how this graph, as x goes farther and farther to the right, notice this graph approaches this line, and this line is actually y equal 3, which I didn't label, but that's what that line is. And then notice this graph, as x goes to negative infinity, notice this graph gets closer and closer and closer to the x-axis. So the x-axis is y equals 0. So that's what visually that's what you see when you have limits at infinity. As x approaches infinity, the function is going to get closer and closer to some number. So now, obviously, functions don't have to approach a number. Like here's a graph. As x gets large, the graph just continues to get large. And here, as the graph gets large, as x gets large, the graph continues to decrease. So you could have, like you had up here, as x approaches infinity, you could have a constant, or as x approaches negative infinity, it could approach some constant. But also, you could have as x approaches infinity, the graph goes to infinity, or as x approaches infinity, the graph goes to negative infinity. So basically, we say the line y equal L is a horizontal asymptote of the graph of f if the limit as x approaches infinity equals L, or the limit as x approaches negative infinity equals L. So up here, we would say that these two horizontal lines are horizontal asymptotes. But for these two functions, we wouldn't actually have, well, this one we wouldn't have horizontal asymptotes. This one might have a horizontal asymptote, but this one doesn't. The first one doesn't. Okay, so one thing to think about is that if you have a constant over x to a power, then the limit of that as x goes to infinity will always be 0. So it says r is a positive rational number. So r has to be a positive rational number. And then it's also true if x goes to negative infinity. So if x goes to negative infinity and the power is defined, because some powers aren't defined for negative numbers. But as long as the power is defined for negative numbers, then the limit of a constant over x to the r is always 0, whether x goes to infinity or negative infinity. So for example, here I have a constant 10 over x to the 5th. As x goes to infinity, I know this limit is going to go to 0. Basically because the bottom is going to just grow much faster than the top. Here I have a constant over x to the 3/4. So here as x goes to infinity, this limit is going to go to 0. Here I have 10 over x to the 2/3. So as this limit goes to negative infinity, this is going to go to 0. What they're trying to be careful of here is you just have to be careful. This is what I said. This is actually the square root of x cubed. Well, for negative numbers, you can't take the square root of negative numbers. So you couldn't even have this function go to negative infinity. So that one would not exist. So, but in most cases, the limit's going to be 0. Okay, so how do you find limits at plus or minus infinity? Well, it's pretty simple. You can read these, freeze the video, and read these 3 statements here, but I'll show you. It's pretty simple. If the degree of the numerator is less than the degree of the denominator, then the limit as x approaches infinity or negative infinity of a rational function is going to always be 0. Now, if the degree of the numerator is equal to the degree of the denominator, then the limit as x approaches infinity or negative infinity is just going to be the ratio of the lead coefficients. So here the degrees are the same, so you're going to get 12 over 3, which is 4. And if the degree of the numerator is greater than the degree of the denominator, you're not going to get a limit. So here the degree is 5 and the bottom of the degree is 3. So you're actually not going to get a limit in that case. And actually that limit would equal either plus or minus infinity in that case. Go ahead and read these others. There's 3 more down here that you can do to practice on, but basically they follow the same rules as far as finding limits of rational functions. So that's what I was doing, finding limits of rational functions as x approaches plus or minus infinity. So be careful though, because here you have 3 here and 3 here, so the degree is 3, but they're the last term, so the ratio is negative 5/3 for this one. So anyway, you can read the others. I'm going to finish this on the next video.